electricity and magnetism is magnetism. That's our final little subunit. So I'm going to take you through the Cornell notes. All of the definitions are in red, and some extra notes I put in there in green. So you want to have it your Cornell notes and copy these down, because you remember you always learn best by writing. So a magnet is a material in which the spinning electrons of its atoms are aligned with one another. And these magnets produce a magnetic force, which is produced by the motion of the charges relative to each other. Even if two magnets are at rest, they're still exerting a magnetic force because the electrons are moving. They're always moving, or you may see the word spinning. And typical magnets are made up of things like aluminum, nickel, iron, and different alloys. And just like electric fields, you're going to see a lot of similarities with magnetic fields. So in electric fields, opposite charges attract and like charges repel. For magnets, opposite poles attract and like poles repel. Magnetism can be defined as the force of attraction or repulsion between magnetic poles, and each end of the magnet is referred to as a pole. You have a north-seeking pole, north pole, and a south-seeking south pole. Now, this is important. You may want to add this in. No matter how many times you break a magnet, there will always be two poles in that magnet. So if you have a magnet with a north pole and a south pole, and I break that in half, now I'm going to have two magnets with two poles. Okay? And when we get into magnetic field lines, that will become a little more clear as well. And this can be confusing, but Earth is a giant magnet, and the south pole of this giant magnet is located at the geographic North Pole. Not the magnetic North Pole, but the geographic North Pole, or the northern end of the axis of rotation. And the magnetic North Pole is located near the geographic South Pole of the Earth. So compasses, they're a device where the magnetized needle can spin, rotate, move around, and it is designed where the north pole of the magnet is always attracted towards the Earth's magnetic south pole. So compasses always point north because they're pointing towards Earth's magnetic south pole, which is the geographic north direction. And the last definition for this page: magnetic fields, just like gravitational fields and electric fields, it's the region where a magnetic force is exerted or any charged object is moving. Okay, just like gravitational field lines and electric field lines, magnetic field lines are imaginary lines, and they map out the magnetic field that's located around a magnet. The lines are always closed loops, and they never intersect. Just like in other fields, the closer lines equals the stronger field, and the lines emerge from north poles and enter south poles. So these are the important rules. So now let's go through some examples. So if we just have this magnet located by itself, the lines emerge from the north pole and enter into the south pole. You can go around this way. It's a nice closed loop. And if we have two magnets together, the lines still emerge from the north pole and head towards the south pole. And if they're located on a curved line, the location of the magnetic field is the direction of the line at that point, or the tangent line. So if we put a point right here, that magnetic field is located in a direction that's pointing that way. Let's finish up. Now, if we have two north poles that are near each other, remember the lines can never intersect and they're going to repel. You'll see some similarities with electric fields. And then if we have two south poles, these lines are going to be coming in to the south pole. And then here, if we have a horseshoe magnet, let's put the north pole on this side and the south pole over here. In between, they're going to be nice, uniform, straight lines, almost like parallel plates. And then outside, they're going to be nice and curved. We want to note about magnetic field strength is that it's the number of magnetic lines per unit area. And remember, that means that the more lines or the closer the lines are together, the stronger the field. And we do draw a magnetic field with arrows, so therefore it is a vector quantity. That I want to make a note of. Last part of the Cornell notes for this unit, so we made it through another packet, is electromagnetic induction. And this is the process of generating a potential difference, think circuits, in a conductor, most likely a wire, due to the relative motion between the conductor and the magnetic field. And I didn't want to define this. I thought it would be better to include a picture. And this diagram shows two magnets and the motion of a conductor. By moving this arrow up, you are crossing the magnetic field lines. So if we were to take this wire and move it towards the magnet, either one, it's not crossing any of those magnetic field lines or flux lines. Therefore, it is not inducing a potential difference. But if I move it up or down and I cross those magnetic field lines, I'm inducing a potential difference. And I could use that potential difference to provide voltage to a circuit. One last thing that we haven't gone over is the direction of vectors. And vectors are drawn with an arrow. So if we picture a bow and arrow from a quiver, it has the tail and it has the point. Now, if we were to shoot a bow and arrow away from us, we would see the tail as the closest point. So if we see a magnetic field like this with X's, that means the magnetic field is pointed into the page or screen. And if it were moving the opposite way, we would see the point coming towards us. So if we see a bunch of points, this would mean that the magnetic field is pointed out of the page or screen. So if I have, let's just say I have, place a wire inside this magnetic field. To induce a potential difference, I can move it left or right, because that would be crossing these magnetic field lines. But if I were to move it up or down, I'm not physically crossing any of those lines, and therefore I would not induce a potential difference. Example problems on what Regents questions on magnets may look like. Now, you may see a few of these on the Regents. It's not a major part of the electricity unit, but it is important, and definitely want to go through some of these. So in order to produce a magnetic field, an electric charge must be stationary, moving, positive, or negative. Now, based on the definition, we know it's definitely moving, and electrons, they do move around, so they produce magnets more. But if there's a single positive charge that's in motion, it can definitely produce a magnetic field. So just by saying positive or negative, that is not enough information. And then number 2, the diagram below shows a bar magnet. What is the direction of the compass needle placed at point A? Whenever I see a question like number 2, the first thing that I want to do is place magnetic field lines here. So remember, they always come out of the North Pole and into the South Pole. And direction of the compass needle, if we think back to the way I defined Earth, the compass needles always point in the geographic north direction, which is the Earth's magnetic south pole. So compasses point towards the south pole. So at this point, the magnetic field line is pointed to the right towards the south pole. So the answer is definitely going to be number 3, which is to the right. Ground below represents a magnetic field near point P. If a compass needle is placed at point P in the same plane as a magnetic field, which arrow represents direction, the north end of the compass needle will point. And remember, compass needles or magnetic field lines are south-seeking. So if the magnetic field lines are moving in this direction, the north end of the compass needle will point in that same direction, making the answer to number 3, choice 2. Number 4, which type of the field is present near a moving electric charge? And if it's an electric charge, there's definitely an electric field. So anything without an electric field, we know to eliminate right away. But if this is moving, it is also producing a magnetic field. If it were stationary, then choice 1 would be the answer. But since it's moving, it's producing a magnetic field as well. It's given 2 pieces of iron and told to determine if both pieces are magnets. And when he touches one end of one piece to the end of the other, the 2 pieces of iron attract. And he reverses one of the pieces again and touches the ends together. And since the 2 pieces attract again, what we can confirm about this is that one is a magnet and one is something called a magnet attractable. And what that means is that it's just attracted to a magnet. Think about magnets sticking to your refrigerator or different things like that. Number 6, diagram below represents wire conductor, positioned perpendicular to a uniform magnetic field directed into the page. Again, these X's mean into the page and dots would mean coming out of the page. And remember, to produce a potential difference or induce a potential difference, what we want to do is move this conductor across the lines. So the only way to do that in this example is to move it left and right. Which point is the magnetic field the strongest, or the magnetic field strength the greatest? And remember, we want to be very close to the poles or where the lines are closest together. So number 7 is definitely B. At point B, the lines are very close together. Number 8, as the speed of the wire is increased, the potential difference will also increase. The slower it moves, the less of a potential difference that will be induced, which is not a vector quantity. Okay, well, we draw displacement with an arrow, we draw velocity with an arrow, we draw magnetic field strength with an arrow. So it's definitely electric charge. You cannot have 7 coulombs west, or it does not have a direction involved with it. And then number 10, we have 2 ring magnets, and we can see that magnet A remains suspended. So if we think back to our free body diagrams from way back in October, gravitational force is always attractive. So that's going to be pointing downwards in this case when we're focused on magnet A. And since it is hovering, we know that this has to be repulsion. So if we want to say force of magnetic force, that is causing it to be pushed upwards. And since it's hovering, those are equal to each other since it's stationary. And like I said, gravitational force is always attractive, and the magnet is repulsive. Therefore, choice 1 is the answer.